All right, hello, welcome back. This is our final video of the semester. I'm super excited. You guys have all worked very, very hard, and I'm all proud of every single one of you. But let's just kind of get right into it. Today, we're going to be talking about RLC circuits, and specifically like sines and cosines and phase angles and stuff like that. So I wanted to kind of start off with plotting sine and cosine graphs in case you're not very familiar with it. So one of the things that is important about RLC circuits is knowing how things change when you add or subtract constants and stuff like that. So sine has a graph that kind of looks like that. Horrible drawing, I know. It starts at 0 and it makes one full rotation like that, and this ends at pi over 2, like here. X equals pi over 2, or 2 pi. Oh my God. So it kind of looks like that. And this is 2 pi. And then, but cosine starts up here, and it kind of goes like, so it kind of looks like this. And then it loops up like that. But it's easy to see that we can very easily create a cosine graph from a sine graph if we would just move it over an amplitude. So that's what you can kind of see here is, instead, if I decided to draw my axis here instead, my green line has become a sine graph and my purple has become a cosine graph. So I really wanted to amplify that changing of behavior. When you go from sine to cosine, you can change it with a phase angle, and that you can just shift it over. So that is how you would think about that. But let's go into a RLC circuit problem. This is from your tutorial, so you should have already seen this, but I'm just going to go through it so that you guys know how to solve these types of problems. And really, a lot of these problems are just going to be plugging in your values that you're already given, but nonetheless, it should be helpful. Okay, so we have this RLC circuit, and it has a resistance of 96 ohms. It has a omega of 377 radians per second. It has a capacitance of 10 microfarads. And then its maximum voltage that it puts out is 170 volts, and it has an inductance of 0.35. So we want to first find the inductive resistance, chi sub L, and the capacitive reactance, chi sub C. So chi sub L is defined to be omega times the inductance. So from here, we know that it is 377 radians per second times 0.35 H. So this gives us a value of 132 ohms. And then our chi sub C, our capacitive reactance, is just 1 over omega C, which we can write as 1 over 377 radians per second. And watch out, our capacitance is in microfarads, so we have to convert that. So it's 10 times 10 to the negative 6 farads, which gives us a value of 265 ohms. So those would be our final answers for that one. So that's kind of how you would solve for that. Next up, we want to solve for our impedance Z. So our impedance is just the square root of our resistance squared plus chi sub L minus chi sub C squared. So we can just plug in those values. Again, like I said, this is kind of just plugging and chugging when you're doing these problems. So we have 96 squared minus 132 minus 265 squared, which equals approximately 164 ohms. And then we want to find the phase angle phi between these. So our phase angle phi, so tangent of phi, is defined as the chi sub L minus chi sub C over R. So that's 132 minus 265 over 96, which gives us, we take the tangent inverse of this, we should get, we should get 0.946 radians. Okay, so the next question we want to ask ourselves is a circuit primarily inductive, capacitive, or resistive? And this is kind of an easy question to answer because we just want to look at our values of the inductive reactance, the capacitive reactance, and our resistance values. So our capacitive reactance is 265 ohms, and our inductive reactance is 132 ohms, and our resistance is only 96 ohms. So our circuit is primarily capacitive. So we want to also we want to determine the I max in the circuit, and then write a formula or write an equation for I of T. So I max, again, this is just very plug and chug type beat. We have our E max divided by our impedance. So you can really think about this in terms of V equals IR. So this is very similar to what our what this is from Ohm's law. So we obviously have this would be our V, this would be our R, and then that would be our current is the same, but we are using different values because we want to find the maximum of it. So this would just be 170 volts over, when I say 164 ohms, which is just 1.04 amps. And so we want to write I in terms of T. And so I of T is a sine function, and it is defined as I max sine omega T minus the phase angle. And in fact, I did a mistake. This should be a negative 9.946 radians, because when we go in here, it's going to be positive. Okay, so we know what our I max is, so we can just put it in our values. So I of T is equal to 1.04 sine. Our omega is 377, or we could just leave it as omega. Minus a minus or a negative 0.946 gives us a positive and it's 0.946 amps. So that is our equation for our current. And so we want to maybe graph these as well. So one other thing that we should look at is the E of T, which is our voltage. So that is just the E max sine omega T. So this is important to note because we have this value right here that is our phase angle. So really these are going to look very similar, but they're only going to be offset by this phase angle. So our E max is going to be 170 volts times sine, and then our same omega, so it's 377 T. So that is our equation for our E of T, our EMF. So our plotting, if we were to plot this, I'm going to make note of some particular, special areas. So I'm going to write this as pi over 377, and this one as 2 pi over 377. And the reason why I chose this is because, so when you do the sine graph, remember, it kind of looks like that. And when it hits this value right here, it is at pi radians, and then this one is 2 pi radians. So since we have this other term in front of it, we need to take into that account. So we divide it out, and that is how you get your frequency. So this E of T, let's do this in a different color. So let's do it in E of T. Let's do it in pink. So I'm going to say that 170 is up here and negative 170 is down here. So this one will look something like this. So it'll come up and then it'll go down like this, and then it'll kind of go up like that. And we can keep going like that. So that's what it'll kind of look like. But then we have this, we want to do I of T as well. So this one, so let's do this in blue. So that is I of T. So it's a different like amplitude, and it's different values, right? But we can still look at them on the same graph. But notice it still has the 377 as the frequency. So we're still going to like base it around these pi over 377, 2 pi over 377. But we have this, this phase angle there. So what that's going to do is it's going to shift it to the, it's going to shift it back actually. So instead of starting at 0, it's going to start about here. And it'll kind of go like that. So let's say that this is 1.04. So we can see that it kind of just, this little 0.946 just shifted it over to the left. So yeah, that is how you would do a solving this type of problem. You should be very comfortable with graphing sines and cosine graphs. If you ever get confused about sines and cosines, you can always just draw like a unit circle and kind of just like label all the points on it. That's what I always kind of do if I forget how, like what sine is supposed to look like. Or what cosine is supposed to look like. I would always just draw a unit circle. It's very helpful. So that is how you would solve that type of problem. I hope that this was helpful to you to kind of see me kind of go through and answer the questions how I normally would do them. I will be hosting a final review session, and it's going to be on Sunday, May 7th, from 2 to 5 p.m. And that will be going over all the things that you need for the final exam. I really enjoyed being able to do this for you guys this semester. I hope that it was helpful, and I wish you best of luck on all your future endeavors and all your future physics plans. I will see you later.